Hi, I'm David. In this fundamental module, I'll be taking you through an overview of the common rail diesel. Common rail diesels are very different to their old mechanical counterpart. They're much quieter, they have much lower emissions, and they have far better fuel economy. We'll be looking at the diesel system and components of these modern engines. In another series of modules, we'll be looking at these components, their circuits, and their operation in much more detail. But for now, let's start our tour at the fuel tank. The fuel tank is the store for the diesel fuel. It differs from a petrol tank in that it doesn't require a large vapour space or an evaporative line. This is because diesel fuel has a higher flash point than petrol. The flash point of a liquid is the temperature at which it gives off vapours that can be ignited. In Australia, the minimum specification is 61.5 degrees C. Many common rail diesel systems use an electric pump in the tank. This pump is designed to provide fuel to the high pressure pump and is controlled by the engine control module via a relay. Clean diesel fuel is essential for today's modern common rail diesel. Some of the filters will remove contaminants as small as 2 microns. A human hair on average is 100 microns. Most of the filters will have a water trap with a water and fuel indicator, as well as a drain for removing the water. Water in the fuel system can lead to corrosion. Also, fungus and bacteria can live in the water and feed on the hydrocarbons of the fuel. Some filters will also incorporate a fuel temperature sensor and possibly a fuel heater. From the filter, the fuel will travel to the high pressure pump. Some of these pumps also incorporate a lift or feed pump to bring the fuel from the tank. The high pressure pump has the task of raising the fuel to its operating pressure, and this could be as high as 2,500 bar or 36,260 psi. Due to this high pressure, appropriate personal protective equipment, such as safety glasses and gloves, should be worn when working on these systems. On the high pressure pump is a fuel metering valve. This valve will control the amount of low pressure fuel going into the high pressure pump, thereby controlling the pressure in the fuel rail. The fuel metering valve is controlled by the engine control module. Some vehicles use a suction control valve for the same purpose. The fuel rail is supplied with the high pressure fuel, and due to its size and construction, helps reduce the pulsations from the high pressure pump. It stores the fuel ready for use by the injectors. The fuel rail pressure sensor is mounted on the fuel rail and provides the engine control module with a signal indicating the pressure within the rail. The rail pressure control valve, if fitted, will be on the fuel rail. This valve performs a similar task to the metering valve, except that it controls the high pressure side of the fuel system and returns any released fuel back to the tank. The fuel injectors are responsible for allowing the high pressure fuel from the rail into the cylinders. The engine control module will provide a control to these injectors. This control consists of one or more pilot injection pulses and a main injection pulse. The injection system also has the capability of supplying post-injection pulses for the heating of the diesel particulate filter, if fitted. There is a fuel return from the injectors, high pressure pump, and the rail pressure control valve. This return line may go straight to the tank or travel via a fuel cooler. The heart of the system is the engine control module. This module receives data from various sensors, processes the information, and then performs activities such as injection control, fuel rail pressure control, EGR, etc. Signals into the ECM include the crankshaft position and camshaft position sensors. This information allows the ECM to determine the exact position of the crankshaft. Engine coolant and oil temperature sensors provide data for various systems like the glow plugs. The mass airflow and inlet air temperature are usually incorporated in the one sensor. Even though the mass airflow sensor is similar to a petrol engine, the information sent to the module is used differently. In a diesel, the amount of air entering the engine will dictate the maximum amount of fuel that can be injected. Remember that a diesel always draws in a full cylinder of air, even at idle. The throttle body is another component that is similar to that fitted to a petrol engine. On a diesel, its function is slightly different. The butterfly does not determine how much air goes into the cylinder, but creates a low pressure so that the EGR will work more efficiently. It also closes off and then reopens when the engine is shut down. Exhaust gas recirculation is an important part of a diesel engine's emission control. The oxides of nitrogen produced by high combustion temperatures need to be removed from the exhaust. One way of doing this is by using EGR. Operation of the EGR system can be either all electric or electric and vacuum. The ECM will determine when and how much EGR is required. The glow plug control unit, which will usually interface with the engine control module, is responsible for the operation of the glow plugs to help starting and reduce diesel knock. Most engines will operate the glow plugs during startup and continue operating them for several seconds after the engine starts. This is called afterglow. The glow plugs have a very low resistance and should not be tested by connecting them to 12 volts. Some manufacturers are now experimenting with pressure sensors incorporated into the glow plugs. This is to monitor cylinder pressure. This will lead to finer fuel control, lower emissions, and even better fuel economy. The turbocharger provides more air into the cylinders so that more fuel can be injected, thereby increasing power. There are two basic types of turbochargers in use on CRD engines. The first is a standard turbocharger that uses a wastegate to limit the boost pressure. There are three types of wastegate actuation: direct pressure, electric, or electric and vacuum. The pressure actuated type is not controlled by the ECM, whereas the other two are. A more common type is the variable turbocharger. These come in different designs. In a variable vane turbocharger, a control from the ECM is used to set the position of the vanes within the turbo, varying the boost pressure. The variable turbos allow high boost at lower engine speeds and lower boost at higher engine speeds, effectively giving the ideal boost for all situations. A variable turbocharger can also assist with EGR operation by creating back pressure within the system. Compressing the air with a turbocharger causes it to heat up. Hot air is less dense than cold air, so it's not ideal. An intercooler is the solution. This will reduce the air temperature, thereby making it more dense. Size of an intercooler is important. If the air is cooled too much, it will lose too much pressure and the gains achieved by the turbocharger will be lost. A boost pressure and charge air temperature sensor will normally be mounted in the manifold. Armed with this information, the ECM is able to adjust the quantity of fuel for optimum performance and economy. When the exhaust leaves the engine, it will pass through a catalytic converter and a diesel particulate filter if fitted. The catalytic converter is usually an oxidising catalyst to reduce carbon monoxide and hydrocarbons. The diesel particulate filter is there to reduce the particulate emission or black soot from the exhaust. The particulates are trapped by the filter and need to be removed by a regeneration process. There are three types of regeneration: spontaneous, which happens when the DPF reaches over 600 degrees C. Dynamic regeneration requires the intervention of the driver to travel at a certain speed for a certain period of time. The driver will be made aware of this requirement by a warning light on the dash. The last is a service regeneration. This will require the use of a scan tool. The DPF differential pressure sensor will indicate to the ECM how successful a regeneration has been. The soot accumulation is determined by an algorithm within the ECM based on operating conditions of the engine, not by the differential pressure sensor. To determine if the correct exhaust temperatures have been reached, there are 2 or 3 exhaust gas temperature sensors fitted in various locations along the exhaust. That concludes our overview on common rail diesels. This module was designed to give you a brief and concise look at the whole system. Check out our series of modules for a more in-depth look at the fuel system, sensors, electronic control, intake and exhaust. Remember, safety at all times. These systems work at very high pressure and are capable of injecting fuel underneath your skin. This is very painful and can take a long time to heal. And always remember, training is the key to your success. Bye for now.